Welcome, everyone. Thank you for joining us for today's webinar on how to leverage PSpice for pre-layout simulation. My name is Supreet Manava. I am a product manager at Cadence for the PCB division, and I'll be your host today. Our speaker today is Himanshu Tonk. He is a lead product engineer for PSpice, and he'll be going over today's presentation on how to use PSpice for pre-layout simulation.
Hello, good morning, good evening to everyone who has joined. And I thank you all of you for taking time and attending this webinar where I'll be going over PSpice simulation and how you can employ that for your pre-layout program processes. I have few slides for you. We'll go over the overview and few challenges for the functional simulation, and that will be followed by a demo where we will perform all the steps of functional simulation. We'll draw up a conclusions and we'll have few time to have a Q&A. So PSpice is an industry grade advanced simulation software. It has been here for more than 20 years. It has been used by many industries as a standard, and it provides a virtual simulation platform where you can convert your design from a concept to a reality. uh, to go over some key few points as an overview. PSpice helps in reducing cost, where you are basically simulating your design and eliminating the need of a physical testing. And this is really helpful when if you mess up your hardware, it becomes a very costly process, and the cost will rise exponentially. Whereas in simulation, you just hit simulate, and if you make an error you can again correct it and hit simulate again. Simulation allows you to run your design in various scenarios, like if you want to test your design at negative temperatures, or if your load is like varying, or if your input is fluctuating, or if you want to see if your design can handle a lightning pulse, for example. You can simulate everything and find your corner cases so that you can avoid the risk of damaging your hardware. PSpice comes with a lot of models, more than 30,000 models, and with precise modeling, you can simulate the design and get the actual data, which is like close to the real world, and it helps you get your design goals readily available. You can also, like when you're doing a simulation, you have to make various decisions like what topology you want to use, what components you want to use, what trade-offs you want, whether you want a really efficient circuit or if you want to cor make corner cutting like costs or losses. So all of this can be simulated, and it can help you develop a structural flow where the decision making becomes efficient. And going over the simulation again and again, there's this kind of iteration that helps reducing time, where if you do all these iteration in a hardware and if you mess it up, you have to develop that hardware again. So simulation essentially saves a lot of time. Now, if you have to do a simulation, there are a few challenges that we pose, that you have to understand a tool and you have to see if the tool has all the functionalities available. Well, PSpice has a very intuitive interface, as we'll see, and it covers all the functionalities which are used in the industry, and it is a complete software package. As I said, that we have more than 30,000 components, so selecting a component becomes easier. You can basically simulate every component, select them based on your needs, and include them in your design. The PSpice has all sorts of simulation settings so that you can vary your temperature, or you can vary the loads, or you can perform Monte Carlo. And simulation where various similar simulator options are also available, so that you can tweak your simulator options for efficient running versus the accurate running. And once you simulate a design, we have a lot of inbuilt measurement functions, so that you can plot your traces, do your measurements, and you can save your window, and you can actually develop custom templates also, which you can use them in other designs. We will see that also. And for what if analysis, like I said, you can vary your load or your temperature, and you can do all sorts of what if analysis and help decide, which will help decide what component and what design choice you have to do. So for the demo, I'll be simulating this design. This is a buck boost converter, uh, basically used in automotive and industrial applications. We will simulate this design. We will develop some models to run them for a functional simulation. We'll do what if analysis. We'll vary the load. We'll do measurements. We'll develop a template. And then we will simulate the same design using a different semiconductor technology to achieve the goal. The goal is to get the maximum efficiency out of this converter. So with this, let's move to the demo. So this is the interface, and this is the design. You can see there are few components missing here. And this is one of the basic and the first hurdle that the designer faces, that he doesn't have a converter. And developing a spice model for it becomes very tricky, because it requires a precise knowledge of all the simulation parameters, spice parameters. And without that knowledge, one cannot do that. So the first problem is solved by a tool which is comes inbuilt, which is known as modeling application. So I've invoked this, and you can see all of these kinds of components which can be modeled by punching in the parameter values. And these parameter values can be either come from the knowledge of the circuit or from the data sheet of the component. So for my design, I have a inductor missing, I have an output capacitor missing, I have a switches missing. So let's do modeling of with that. I'll place an inductor. So this is the interface, and you can see that I can mention all the values like inductance, tolerance, or initial current flowing through the inductor. I can define the parasitic elements or the temperature and current coefficients. So for my design, I need a 10 micro inductor with a series resistance of 0.025. I'll place this. Let's place a capacitor as well. So this comes with similar interface where they have little more parasitic elements like a series inductance as well, apart from the resistances. I have the temperature coefficient and the voltage coefficient for this. So for my design, I need a 220 microfarad capacitor with a series resistance of 0.012. I'll hit R to rotate the symbol and place it. Now I'll need MOSFET. So I'll invoke the modeling application for MOSFET. I can select the channel, what channel I want, and I can punch in this device specification. And if you notice these device specifications, they are mapped directly to the data sheet, like the capacitances, the drain to source voltage, on state resistance, gate resistance. There are diode characteristics as well. So for this, I will choose a MOSFET, which is this. This is 75 volt drain to source voltage MOSFET. And I can find the parameters like which we talked about. The on state resistance is here, gate threshold voltage, the capacitances, the gate charge, and the body diode characteristics. So I can just input these values directly. So let's do that, starting with capacitance. So 196, 2900. Output capacitance is 370. Drain to source voltage, we saw that 75. The resistance is 0.012. And these can be typical values like you saw in the data sheet, or these can be maximum or minimum values as per your choice. I'm taking the typical values for this. (41 nano). So once I hit place, what is happening behind the scene is a SPICE model gets generated, gets attached to this circuit, attached to this component. Its SPICE model is attached in the simulation settings as well. And now this MOSFET is simulation ready. And let me copy paste this MOSFET because I want two of them. So my circuit is complete. And modeling application makes it this much easy where you can just punch in the values and your simulation models get attached to the symbol. So let's run the simulation. Okay, I have some mistake here. This is a model which I attached previously. Yeah. So while it simulates, let me go over different components which you can model. I have a power diode, and you can see the breakdown voltage here, junction capacitance, forward current. All these values they can place directly from the data sheet, and you simply place it in your design. I want to show you transformers. So transformers share common parameters like winding resistance, winding inductance, the primary and secondary winding resistances, turns ratio, and leakage inductance. And you have a two winding. You can select a custom tap where you can define the tap percent for the primary and the secondary. Then I have a center tap with a leakage inductance where I can do a primary tap or secondary tap or both of them. I have a flyback configuration with the inverted dots, a forward configuration, and a forward with a reset winding. We also have digital components. So let's see them. This is an AND or NAND gate where I can define a number of inputs, which can be many. I can define a number of outputs, which can be Q or Q bar. Q bar will make this a NAND gate or both. I can define the number of inverted inputs if I want. Then I can define the propagation delay from input to the output. And these are common IO parameters like threshold voltage, output input resistances, and output maximum high and low voltage levels. Let's see one more SR flip-flop with a reset. So here I have more parameters to define, uh, like a triggering condition, whether I want a rising or falling trigger, initial condition of the outputs, set reset levels and type, whether I want asynchronous or synchronous. Then I have timing model parameters, and then the common IO parameters which we see. So modeling app covers all sorts of components, and you can just punch in the values and use them in your design without worrying about the SPICE knowledge or the SPICE parameters and tweaking them. So our simulation is completed. So let me place a voltage marker at the output, brightened by green, and this is my output voltage. So let's add few more plots, and I can either place the marker in the circuit or I can add the traces from here as well. So I want to see the inductor current. This is how it looks. And I want to see MOSFET current. Yeah. So this is the whole transient simulation. Now, if I want to see the steady state values, so let me adjust the axis. I will set it for 3.3 milli to 3.4 milli for the steady state. And these are the zoomed in values for the output voltage and the inductor current and the MOSFET currents. Next, let's add some measurements. So for that, we have evaluate measurement. PSpice comes with all of these inbuilt measurements, which cover variety of functions, which you can select from here. And these are the traces which are available in the simulation. So you have to just select the function and the trace and you get the measurement. So I want to find the maximum current for the simulation. So I'll select max and then the current, and it gets added here. Now suppose I want to find the maximum current at steady state. So for that I have max X range. So I can define the X axis range. So I'll select the trace, then I'll define 3.3 milli to 3.4 milli. So the overshoot value was 5.64 and now the steady state value is 4.67. Let's find the inductor current ripple. So what I'll do is I'll do max X range for inductance. And what I'll do is subtract it with the minimum range. So the maximum value minus the minimum value will give me the ripple. So 3.3, 3.4. Let me zoom this in. So I'm getting a ripple of 3.42. And similarly, I can find the maximum ripple for output voltage. So for that, let me find the trace. I can search the trace from here. Minus the minimum value. So this is my output ripple coming on. So this is how easy it is to add your measurements and see the results in one window. Now, suppose I want to simulate it again, or if someone else want to simulate it again and want to see the same things. Now, rather than repeating the same things, what I can do is I can save this display using a display control. So what it allows me to save this display in this format. So I'll give a name like SMPS waveform and measurement. I'll hit save. And the next time the simulation is run, one can invoke this and select this and hit restore, and it will restore this view for them. So it avoids the repetition of doing this again and again. Another use case comes is when suppose I want to see these waveforms for a similar circuit. For that, I can create a template. Here, there are various templates which are shipped for the single run or the multi run, and I can define again my own custom template. So I'll give a name. I'll do a save to. Here I can save this template for a local file so that it will work on this project, or I can save it globally so that it will work for all the projects that I work on. So let me give a description. I'll hit next, where it will ask me to define the node name, the type, and the description. So let me quickly type this. I'll do finish. So an SMPS template has been created. Now to see the utility of this, let's return to capture. And I have a different design, an SMPS design of a forward converter. So let me run this first. Progress bar at the bottom shows the progress. So it got simulated. Now to use that template, I have to use something called a template marker. This is showing all the templates that we saw earlier. And I have the SMPS waveform template. I'll do a place. I'll get a marker, a voltage. And by the way, it shows it indicates where to place the next marker for me. So I'll place a next marker for my inductor current, and then it's a MOS drain current. So let's place it here. It's got highlighted. And if I come here, I see the same waveforms and the measurement for a different circuit, output voltage, inductor current, and the MOSFET current with the ripple and output ripple and inductor current ripple here. So this is how you can use a template, and it saves a lot of time, and you can create any number of templates depending upon your requirement. Now, returning to our own design, what I want to do now is let's do an what if analysis where I will do a sweep analysis. So first let me run the circuit. Yeah, while it runs, I'll show you what I have done. So what I'm doing here is I'm doing a parametric sweep for the parameter load. Load is here. I'm sweeping my output load for these values of resistances. And PSpice comes with a whole series of whole range of sweep variables, like you can sweep a voltage source or a current source at the input or anywhere in the circuit. You can sweep a model parameter. So if you want to sweep a model parameter, let's say of MOSFET, you can define the MOSFET type and the name, and you can sweep them for linear or logarithmic or the value list. Or you can sweep the temperature as a parameter. You can run the simulation in a specific temperature as well, or you can repeat the simulation for temperature values. And for Monte Carlo, we have specific tab where you can define the number of runs. You can define the distribution, whether uniform, Gaussian, or any custom distribution. You can define seed number, and you can run the Monte Carlo analysis where the component values will be varied within their tolerance range to give you a Monte Carlo run. Now, one of the exclusive features of PSpice is that because all these sweep analysis runs, they are independent of each other, because the value of 3 ohms is running a circuit and then value of 5 ohms is running a circuit. They are all independent of each other. So these can be run in parallel. And this is something that is not offered by any of the Spice tools out there. And it helps in saving a lot of time. And to invoke this, you have to use this option like enable parallel param sweep. And depending upon how many compute cores you have, all those cores get utilized, and each of these individual runs are run at a specific single cores. They are run together in parallel, and the result is then merged together, and it leads to a lot of savings in time. So returning to our simulation is complete. I'll select all of the sections. It has taken around 116 seconds here. So let's quickly compare this with the serial simulation that I ran. So I have saved the output file for that. Let me zoom in. It took around 234 seconds. So I'm saving around twice the time here. And this is one of the exclusive things about running parallel simulation. And in fact, we ran the tests on different kinds of circuits and we have the result for them. So this is the results where we ran a PWM inverter, a op-amp circuit, different kinds of SMPS designs, an audio amplifier, and we ran for parametric sweep, a Monte Carlo, or temperature sweeps. And we compare the results for two machine sets, where one machine was a 6-core machine, the other machine was a 32-core machine. And depending upon the complexity of the circuit, we got the performance improvement of around 8 times. So this is really something that helps you save your time while doing the what if analysis kind of situation. So let's see the results, and let me use the display control here because I have saved the results in that format. So this is the format I was talking about, where I can see the waveforms and the measurements here. And these are same measurements like inductor ripple and output ripple. And I can see the output voltage just shy of 12 volts. Inductor current is here, load current is here, and this is something that looks good to me. Now, what if I want to see how my inductor ripple is varying when the load is varying? So for that, let me open a new window, and we have something called performance analysis. And what it does is you can change your x-axis to the parameter which is varying. So in this case, the load parameter which was varying, I can make that as an x-axis, and I can plot my measurements to see at which load what was my inductor current ripple or output voltage ripple. So let's add a measurement here. So for starting, let me add a simpler measurement like a maximum of inductor current. I selected the maximum function. Now I can select the trace. So IL1. So it made the expression the next. And now it is showing me where it has found the maximum current. It is around 5.66 like we saw that earlier. And I can select next. And now it plots the maximum inductor current against the load parameter which was varying. Similarly, I can add another measurement. So let's add the inductor current ripple. So I'll use the same formula again, where I will subtract the minimum from the maximum. So maximum minus minimum, this is the inductor current ripple. It is varying like this, around 3.4 to 3.38. Let me add another plot for output voltage ripple. So let me find the trace here. Minus the minimum value, 3.3 milli to 3.4 milli. And this is my output voltage ripple, which is not varying that much, 42.8 milli. So not only that I can add measurements, I can also visualize the measurements in this manner. Okay, now let us return to the circuit. And what I have is I want to simulate my design using a different semiconductor technology, like I said earlier. So I have a circuit where I have used the GaN MOSFETs. Let me open that. So you can see U2 and U3. These are GaN MOSFETs that I have used. So let me run the simulation. Okay, it has the missing models. So let me add the model. Okay, let me, and so I have a missing model. So what I can do is I can go to its website and find the model. And to see that, we have this PSpice modeling website where we list all the models which are available with our design, with our installation. These are shipped free of cost with the installation, and these are defined in these many categories. So like I can go to a discrete, a MOSFET, and I can find a power MOSFET here. So this page will load. And you can find all of these MOSFET within the installation. And other than that, we have also collaborated with manufacturers which ship all these designs, all their spice models, sorry. So let's go to one of them. This is EPC. So I was trying to find the design for this one. So let me find the model. So I can just search the model which I want to find, and I can download this spice file. Let me rename this. Let's go to a circuit and use this library file so that actually the design can run. Yeah. So while it runs, so these manufacturers, they have all of these models in one place. Let's see another manufacturer, which is Toshiba, and you can find the models directly here, and you can download them as per your wish. And the other thing is Murata, where you can download their ceramic capacitor and power inductor models, RF inductor models in one go. And using GAN, why I'm using GAN is because they are known for their high switching frequency and very low losses, and that helps me in saving a lot of losses, getting a lot of efficiency out of my design. And for this design, I had to like download and use it in a design. I have already used the symbol, but for another design, let's say I have this design which we saw earlier, I have the symbol and I want to use that design. The one more way is to use associate PSpice model. So I can select the mouse, I'll do a right click, associate PSpice model. It will ask me if I want to associate or not. And here I can directly go to the model which I have saved in my design. This one. It shows me the model text, what is written inside the model. And I have to do a model mapping for symbol to the model terminals. So I'll do a source in here. For G, it is gate. For drain, this here. I'll do update selected. When I do this, this model, this component gets modified with the spice model got attached to it, and the simulation model got also added in the simulation settings here. So I don't need to like navigate and add it to here for the simulation. So returning to our circuit, let's see. Yeah, it's around 89%. So for this circuit, what I have done is I'll be using the template markers again, where we will see the output voltage, the inductor current, and the MOSFET current. So yeah, it got simulated. Let's use the template marker so that I don't need to like redo everything. Place it here. Then I wanted inductor current, then the MOSFET drain current. Coming in here, this is the waveforms that it looks like with the inductor currents ripple and output voltage ripple. And if what I've also done is to calculate the efficiency, because what I've done is I've replaced the MOSFET which I use in my previous design with the GAN ones. I have saved another display which was calculates the performance. So let's restore that. So at the bottom, I have calculated the MOS switching losses. At the middle, there is input power, the output power, and the efficiency. And using this, what we have found here is I am getting an increase in efficiency of around 4%. So in conclusion, when I replace my silicon MOSFET with gallium nitride alternative, I'm saving around 2.82 watts. which is around 33 watt hours if I use this converter for 12 hours daily operation, which leads to an yearly saving of 12.3.5 kilowatt hours. And if this is again, if it is installed in 1 million devices worldwide, I'm saving around 12 million units. So I am I have achieved my goal of getting the maximum efficiency by using this. To conclude, we saw the whole functional simulation where we model the circuit, model the components. Using the modeling application, we punched in the values directly and used in our simulation. Then we observed the results, we made some measurements, we saved the design, we saved the plot windows and used them in another design. Then we sweep the values for different loads and did the what if analysis if my load varies. And then we change the circuit MOS, MOSFETs with the GAN alternatives to achieve our goal. This completes my whole demo. And now we can open the forum for Q&A. Thank you.
Yep. Thank you, Himanshu.
Thank you.
So let me start with this question. We have, can PSpice simulate for total PCB power consumption in pre-layout?
If you have defined all the PCB trace uh, uh, all the PCB trace losses in your SPICE model, you can essentially calculate them. Yes, you can do that.
Okay. All right. It looks like this person is asking, can I use system capture for PSpice simulation?
Yes, we have also, so we have two front end tools. This was ORCAD capture, and we have also have system capture, and you can run PSpice simulation with that also.
Perfect.
Yeah.
Okay, a question on modeling. How do you link a model to a symbol and then place it in the schematic? Where would that
Uh,
process be managed?
like I showed you, you can, if you have the symbol already, you can already do a right click and associate a PSpice model where you have to have the model spice definition in your disk. You can just navigate to it and make sure that all the symbol pins are matching and mapped to the model terminals in the spice. And there is also a modeling editor tool where if you develop a model and you so from there you can actually create a symbol or attach another symbol through it. So there are various ways to do it. Whatever situation arise, you can do that.
Okay. All right, this person is asking, can you run multiple scenarios with different sets of parameters? And they want to clarify not a Monte Carlo, but maybe you have a specific subset of parameters that you want to vary the values for. Can you do that?
Yeah, you can do that. You can do the parametric sweep, uh, but it can be limiting. So we have also an advanced analysis parametric plotter where you can vary multiple parameters in one go. It comes with an advanced analysis package, which was not covered here, but you can do that.
Okay. All right, how do you fine tune PSpice models to get accurate results? And any recommendations on how to decide between minimum, nominal, or maximum values?
Uh, Considering the minimum, maximum, and nominal, it depends on how the manufacturer is recommending. And usually, what people do is they take on the nominal values and go with it. Some like to do the maximum values because they want to see the maximum range out of it. And to fine tune your model, we have a model editor where you can define the curves, the characteristic curves for, like, let's say for a diode, you can define the forward and the reverse and the charge characteristics. And you have to input the values based on which it will generate the curves. And when you generate the curves and you are okay with it, you can extract the model so that it will tweak the simulation, not simulation, sorry, spice parameters based on the curves. So there are various ways to do that.
Yeah. All right. Are changes made in the test bench reflected back to the base schematic?
Uh, when you create test bench, it simulates separately, and it's up to you if you want to include them in the schematic, you can do that.
Okay. All right. How can PSpice be used to detect over voltage conditions and part reliability?
Uh, over voltage conditions, for the reliability aspect, we have an advanced analysis tool again, which is known as smoke analysis. Uh, and again, it will also use the voltage conditions as well. So for that, you have to define the smoke parameters for each component, where you can define the maximum voltages each pin can take, or the thermal values that it can take. And when you run the simulation based on the smoke parameter values, the smoke analysis will run its simulation, and based on the temperature rise, it can show which components are stressed and what kind of stress it is. Is it a temperature stress or a voltage or a current stress? So you can do that.
Okay. All right. I think you might have just answered this, but does it give component temperatures?
Yeah, it gives.
All right. I think several people asked something along these lines, but can you do the simulation on individual blocks or subcircuits and not the complete system?
Uh, so we have a test bench feature where you can uh, develop a not develop you can select a part of your schematic and run that. If you want to like simulate different blocks, you can create different schematics for that, and then you can develop a base schematic where you can call all the blocks or like include all the blocks so that it will be a complete simulation. But to run in them individually, you can create a separate schematic and they will have separate simulation profile, and you can run them individually.
Okay. All right. Can you use standard SPICE and IBIS AMS models as part of PSpice simulation?
uh, we do support IBIS models, where these IBIS models are converted into the SPICE models, and it is done using the model editor tool again. And for ADMS, we also support like a digital modeling interface, uh, where you can use a Verilog A models. You can develop more Verilog A models in the model editor and include them in the SPICE simulation.
Okay. All right. I wish to ensure any modeling has no connection with the circuit or PCB design. Is that something that will be supported within PSpice?
Sorry, I can you repeat that?
It says this person says they wish to ensure modeling has no connection with the circuit or PCB design. So maybe doing the simulation but not connecting it back to the schematic. That's my interpretation. Is that something that we can do?
I'll have to get back to actually, I don't understand it completely. You want to separate the model with the PCB. I
Yeah,
mean,
maybe. Yeah, that was your question, feel free to add in another question to clarify.
yeah.
All right. Can we use PSpice for high-speed simulation like PCIe Gen 3 or 4? Um, what is the highest frequency, for example, that you could simulate for a diff pair?
Uh, that is kind of something that I'll have to get back to you. But I feel, I mean, the PSpice is a complete tool where you can do a complete mix level simulation. So I think it should be possible, but to get to the specifics, I'll have to get back to you. So yeah.
Okay. All right. All right, I think somebody's asking about IBIS AMS models once again. I think Himanshu already said you can go into the
Yeah.
model editor and uh, assign models to
Yeah, if you have
different
like IBIS
components.
models, you can
Yeah.
convert them into Spice models. Yeah.
Yep. Okay. Perfect. All right. I think I'm seeing that's the end of the questions that we received during this. Or we got a couple more that are just coming in now. Can we simulate RF, LF, and BLE communication antenna parameters using PSpice?
I believe if you have the Spice model for them, you can.
Okay. So it's model
Yeah.
dependent.
Yes. You need Spice models for that. But that is true for like any tool. So if you have the models, you can.
Yep. All right. And I think that wraps up the questions that we received during the session. Thank you all for the interactive questions. Thank you for attending today. If you liked what you saw here and would like to attend future sessions, we've got another
Sorry.
webinar coming up
Yeah.
on August 13th about how to improve PCB signal and power integrity with integrated layout analysis. So we hope to see you there. Thank you.